In our last video, we built a model that fit our data perfectly. We found the optimal line using geometry. But imagine a student who scores 100% on every single practice exam. They seem like a genius. But then you give them a final exam with the questions they haven't seen before, and they fail miserably. Why? Because they didn't learn the concepts, they just memorized the answer key. In machine learning, this is called overfitting. It is the most dangerous trap in data science. Today, we are going to learn about how to detect it and how to prevent it using the golden rule of machine learning, the train test split. Welcome to Decoding Complexities. I am Pradeep. To understand overfitting, we need to understand what data actually is. Real world data is a combination of two things: signal and noise. The signal is the true underlying pattern, the relationship between studying and scoring. The noise is the randomness, like lucky guesses, bad sleep, measurement errors, and so on. Our goal is to find a model that learns the signal and ignores the noise. But if we force our model to try too hard, if we give it too much complexity, it will start to connect the dots perfectly. Look at this. The error on our data is 0. But this model is useless. It has learned the noise. If we show it a new student, its prediction will be wildly wrong. So, how do we stop our models from cheating? We use the train test split. We take our dataset and we surgically divide it into two visible vaults. Vault 1 is the training set. This is usually about 70 to 80% of the data. We give this to the model. We let it see these points and learn from them. This is the study guide. And Vault 2 is the test set. This is the remaining 20 to 30%. We hide this from the model completely. This is the final exam. Once the model is trained, we unlock the test set and ask the model to predict those values. If it performs well on the hidden data, we know it hasn't cheated. We understand the philosophy. Now let's see the implementation. In the real world, you don't get green dots and red dots handed to you. You get a raw, messy list of numbers. We are going to jump into Python, take a raw dataset of 100 students, and physically implement this vault logic using the industry standard library Scikit-Learn. First, we import our tools. We import NumPy for the data arrays, Matplotlib to visualize the vaults, and train test split from Scikit-Learn to do the heavy lifting. Here is our raw data. We have number of hours studied and their exam scores. Let's visualize this data. This is our reality, just a list of numbers. Now we apply the golden rule. We split this data. We use the function train test split. We pass in our arrays and we set test size equals 0.25. This means 25% of the data is held back for the final exam. Let's visualize exactly what this function has done. We plot the training examples in navy blue and the testing examples in red. These are our vaults. The blue points are what model will see. The red points are what we are hiding. Now it's time to train. We create a linear regression model. Notice the critical detail. We call the fit method passing only the training data. The model has learned. It found an intercept and a slope based on the blue dots alone. The model is trained. Now comes the moment of truth. We need to see how it performs on the data it studied versus the data it has never seen. We ask the model to predict on both sets. To score the model, we measure the RMSE, the root mean squared error. This tells us, on average, how many points our prediction is off by. Look at the result. The training error is about 10.59 and the test error is about 9.50. These numbers are comparable. This is the sign of a healthy model. It means we have learned the general signal, not just the random noise. If the training error was 1 and the test error was 20, that would be the mathematical proof of overfitting. Finally, Let's look at the result visually. We plot the regression line against both datasets. The line cuts perfectly through the center of both clouds. Even though it never saw the red dots, it knew exactly where they should be. That is the power of a generalizable model. This concludes our arc on simple linear regression. But linear regression assumes the world is a straight line. What happens when the data is curved? What if studying too much actually lowers your score due to burnout? In the next video, we will break the linearity assumption and enter the world of polynomial regression. If this deep dive was valuable, check out the detailed companion blog post and the Google Colab notebook linked in the description to run this code for yourself. Hit that like button and subscribe as we continue to decode the complexities of machine learning. Thank you for watching, and I will see you in the next one.